Hello there! This video is going to show you how to level up your correlation analysis by doing regression and multiple regression analyses. So what you do with regression is you can plug in multiple quasi-independent variables or a quasi-independent variable and a control variable to predict your dependent variable with multiple regression, or you can do a simple regression where you just have one quasi-independent variable and your dependent variable, and I'm going to show you both. At the end of the day, regressions will give you an equation that you can use to make predictions about the dependent variable in your population based on any value of the quasi-independent variable that you want to plug into the equation, and those predictions are based on your sample data. The stronger your correlation is, the more effective your regression-based predictions are. So we're going to start with just one factor regression analysis with just one quasi-independent variable and then move into more complex designs. And I'm also going to show you how regression looks in an actual published journal article. Then we're going to get into some advanced regression analyses that are also in the article, looking at moderation and mediation analyses and results. So again, when correlational research is used to make a prediction about a criterion variable, right, your y variable or your dependent variable or your outcome, and those predictions are based on your predictor variable, which is your x variable or your quasi-independent variable, then you need a regression analysis and a regression equation. And again, multiple regression can be used when you want to examine the relationship between the quasi-independent variable, your x variable in correlational research, and your dependent variable or your y variable, while also controlling for other co-occurring variables, which we'll call z variables if we're treating them as a control. Or you can use regression, multiple regression, to see how two or more quasi-independent variables or x variables interact to predict your dependent variable or y. Here is an example of correlational data that's designed to measure the relationship between x, our quasi-independent variable, is expected grades, and y, our dependent variable of actual earned grades. So on a quiz, back in the day, I had students put their expected grade on the top of the quiz before they handed it in, and then I looked at their actual earned quiz. So see the scatter plot there, and notice that each dot represents one person's expected and earned grade. So that first dot on the left there, you see they have an expected grade of 25 and an earned grade of 35. So I used Excel to analyze this data and found a correlation that was strong and positive of 0.66, which suggests that people who expect higher grades tend to get higher grades. And people who expect lower grades tend to earn lower grades, right? Positive relationships means X and Y tend to go in the same direction. And you can also tell this by looking at the scatter plot. Notice that the dots are clustered, meaning that they're kind of close to a line, so that's strong, and they go upward, meaning it's a positive correlation. Notice, though, that the correlation is strong, but it's not perfect. We don't have a correlation of 1 or -1 if it was a negative relationship. And notice that the student in the second row of data expected a better grade than the student in the first row, but they earned a lower grade than the student in the first row of data. This type of imperfection will lead to some error in our regression-based predictions, but it's still really useful. Now let's focus on the line and the equation for the regression analysis. So based on my analysis in Excel, I found a beta or a slope coefficient of 0.613. This is the value that will be multiplied by any value of x, whatever you want to plug in for your quasi-independent variable, and then you'll use that to make predictions about your y, your dependent variable. So you could plug in any value for expected grade in this equation for x, and then it'll spit out a projected or a predicted earned grade on the quiz based on what they expected. Notice that the notation for the predicted values of y is y hat. It's got a little hat on top of it. And look here, this beta, this 0.613, suggests that for every 1 point increase in expected grades, you will predict a 0.613 point increase in earned grades. Now, if your beta, if that 0.613 was negative, then that would mean we have a negative correlation. So if your correlation is negative, then your slope or your beta is going to be negative. And that would suggest that as x increases, y tends to decrease. But in this case, we have a positive value. Now, the value that you add at the end of the regression equation is called the intercept, or the constant, and it's really the starting point for predicted values of y if x equals 0. So think about how the math would work, right? If x was 0 and you plug it in, you would have 17.534 would be your value. So in this equation, someone who expected a grade of 0 would be predicted to earn a grade of 17.534. Then the predicted value of earned grades goes up 0.613 points from there for every additional quiz point grade that the student expected. So this regression equation can be used to plot a regression line that you see there that represents all the predicted values for your dependent variable, for your y, based on any value of x, your independent or quasi-independent variable. So for example, if I plug x equals 40, well then that would be 40, I expect 40 points on the quiz, and I plug that into the regression equation. Then if I do the math, I get a predicted y of 42.05. Predicted points earned on the quiz. And you could just see that that's going to correspond to this dot right here that's kind of pointed there. And now I could just make a few more predictions with the equation and then plot my dots there and then use that to connect the dots for that line. You can also add a trend line to any scatter plot using the chart elements in the design in Word or Excel. So in chart design, you'll see chart elements and you can add a trend line. And that's actually what I did to get that line. But you could prove that the dots, everything that you would plug in for X into that equation, you could fit it on that line with the predicted Y. So keep in mind that we really don't need to make predictions about earned grades based on expected grades for our sample members that you see there in the dots or in the data. We already know their earned grade. The point of a regression equation is to use the sample data to make predictions about the population beyond who was in the study, which is really, really useful. Here is another example of a regression equation for correlational data. Now we want to predict work performance rated from 0 to 7 by managers for engineers using their college GPA. Because an engineering firm is considering using college GPA as an employee selection criteria, and they want to make sure it has criterion validity, or in other words, it predicts performance. So the correlation for this data is 0.66, again, which is weird, but it is, and it is strong and positive. So it suggests that engineers with a higher college GPA tend to have better performance, and engineers with a lower college GPA tend to have worse performance. This regression equation suggests that we can expect a 1.375 point increase in performance for every 1 point increase in GPA, right? That beta, that slope coefficient in front of the x. And our intercept or constant tells us there at the end that someone with a GPA of 0 would have a predicted performance score of 1.813. So that's kind of like our starting point for performance, and it only goes up as your GPA goes up. Because this is a strong correlation, most of the dots, the sample data, are really close to the line, those predicted values of y based on x. You can also confirm that the line represents the equation by plugging in various values of x. So for example, if I plugged in x equals 2, 2 times 1.375 is 2.75. Then you take that 2.75, add it to 1.813, and you get 4.56, which would be the predicted performance if someone had a GPA of 2, for example. Now let's shift our focus to multiple regression. Multiple regression can be used to examine the relationship between two variables, x, your quasi-independent variable, and y, your dependent variable, while controlling for an extraneous variable, which we usually call z. Any variable that we're kind of trying to control for, but it's not necessarily an independent variable or quasi-independent variable in our hypothesis, we call it z with correlational data. If both variables, x and z, are significant predictors of y, you can make a regression equation with a beta coefficient for x, the predicted change in y for each 1 point increase in x, and a beta coefficient for z, the predicted change in y for each 1 point increase in z, and then the intercept or the constant would be the predicted value for the intercept or constant would be the predicted value for y when x and z equals 0. Researchers also use regression equations to make predictions about dependent variables, or y variables, based on many quasi-independent variables, or x's. For example, multiple regression equations are used to predict insurance risk and set prices. So prices would be your y, your predicted y value, for premiums based on many x variables. So when they're figuring out how much of a risk you are and how much they should charge you for insurance, they're probably using a regression equation that includes variables like age, gender, credit score, number of DUIs, number of traffic citations, and etc. Maybe the kind of car you have, things like that. But those would all be kind of considered quasi-independent variables that are used to predict your Y variable of premiums. Just like with correlation analyses, regression is really based on looking at your p-value and your effect size. So remember, the p-value tells you the probability that your results are a fluke. The probability that the relationship that you observed is just due to random variance, random noise, pre-existing differences that have nothing to do with the relationship between the variables that you're looking at. So if you get a p-value less than 0.05, that means there's less than a 5% chance that that relationship that you're looking at is flawed or isn't real. And also that it's due to error. So if you get that low p-value, kind of our standard in behavioral sciences is a 5% chance, or p less than 0.05, that means you have significant and reliable results. And keep in mind that it's easy to get significant results with large samples. So it's really also important to look at effect size, because just because there's a reliable relationship or a consistent relation, a reliable relationship or a significant relationship doesn't mean it's super consistent or that it has a really large effect size. So just like with correlation, we look at R squared as our coefficient of determination for regression, but you'll see it as an uppercase R squared usually. And usually that suggests that we're looking at the percent of variability in our dependent variable that's accounted for by multiple different predictors, either all of our X's, if we're looking at a bunch of quasi-independent variables, or our X and then all of our control Z variables. If you see a little triangle in front of R squared in a table, that means that's the change in R squared. So when you run a regression, you usually do it in multiple steps, where you start with your independent variable or your control, and then you kind of build and add more variables into your models. That change of R squared just tells you how much your predicted variability in Y increased or changed with each additional variable added to each model. So yet again, here's kind of a summary of how to make sense of a journal article if you're reading it for your own sake, or you're developing an annotated bibliography, or you're just trying to summarize research and make sense of it to state hypotheses, or just develop best practices for whatever you're doing in your job or your life. So you can kind of go through this on your own. What I want to focus on, in my opinion, is the hardest part, which is figuring out the key findings for your hypotheses and making sense of the results. So I will take you through some examples of how to make sense of results in regression in a real journal article. So yet again, we're going to be looking at Why Me, the frog pond effect, relative deprivation, and individual outcomes in the face of budget cuts, that I co-authored with two of my amazing colleagues, Lee Sing Jean and Tahara Probst. They're awesome, and I still work with them today. So if you haven't already in the previous videos, go ahead and take a moment to read the abstract so that you can make sense of the study and kind of know what's coming. So just go ahead and pause this and give this abstract a read. Now, typically, statistically significant results with a p-value less than 0.05 are notated with asterisks, like you see here, like the little stars. And at least one asterisk equals significant if our criteria is less than 0.05, because you'll see down here, if p is less than 0.05, it has one asterisk. Now, if it's less than 0.01 or 0.001, it's still less than 0.05, so one or more asterisks counts for us. And then if you see that little T up there, that means that it was marginally significant with less than a 10% chance of error being involved. So the first model, A1 and B1, in a multiple regression analysis typically only includes the primary independent variable. So in this case, personal impact of budget cuts. And that model is designed to make predictions about the dependent variable, which in this case would be job satisfaction for the model A's, and effective commitment or emotional attachment to the university for the model B's. The next model, A2 or B2, includes the other independent variable or the control variable, which in this case, we're looking at another independent or quasi-independent variable, which is the departmental impact of budget cuts. This model allows you to examine the relationship between one independent variable and dependent variable while controlling for the other independent or quasi-independent variable. Notice there's an intercept, and that is the A in the regression equation, and that's at the end. So the intercept is the starting point. Remember, that's the constant, the starting point for the dependent variable if the values for all independent variables in the model equal 0. So for instance, if there were no individual or departmental budget cuts, we would predict that employees would have a mean job satisfaction rating of 2.07 on a 3-point scale and mean affective commitment rating of 3.99 on a 7-point scale. Now, I typically focus on results from the latest analysis with the most variables, and I look at the direction of the beta coefficients in the model to determine the direction of the relationship between the criterion and the predictor, like correlation. So allow me to demonstrate. If you see my boxes there, I'm going to focus on the regression coefficients for the independent variables in model A2 and model B2 before we start to get into model 3, which is looking at the interaction or the moderation effects. These are looking at the main effects here in model 2. So if you look here, we see that more individual level budget cuts, which is PI, that personal impact, were a predictor of less job satisfaction, right? Because we've got negative coefficients. And more individual level budget cuts were a predictor of less affective commitment, and that's after controlling for departmental budget cuts, or DI. Now, if we were just looking at model A1, we wouldn't be able to see the relationship between individual level budget cuts and outcomes while controlling for departmental level budget cuts because that hadn't been entered into the model yet. So that's why we're focusing on model 2. However, if we look after controlling for individual level budget cuts, departmental budget cuts are only a predictor of less affective commitment, but not job satisfaction, because you notice the stars go away for model A2. You don't see any stars with departmental impact. Now, if you look down here, you can see that the explained variance in the dependent variable with the independent variables in each model. So this is the effect size, or R squared. So here in model B2, we see that individual and departmental level budget cuts combined predict 9% of the variability or differences in affective commitment. Now, this is a small percentage, but it still constitutes a medium effect size, predicting almost 10% of the differences in the dependent variable based on 2 independent variables. And that's still impressive, because think about all the other factors that influence affective commitment and that will predict the remaining 91% of differences in affective commitment. So again, that explained variance is like your R squared, and it tells you what percentage of all the differences in your dependent variable, right, the stuff that's listed up here, is due to everything that's plugged into your model so far. Here we have table 3, and it shows the results for the dependent variables of psychological contract breach and turnover intentions that you kind of see up here. Those are always where your dependent variables will go. Forgive my funky line, my goodness. So this is again looking at psychological contract breach or broken promises and turnover intentions wanting to quit. Now focus on the asterisks and allow me to demonstrate results for the main effects again by focusing on the regression coefficients for the independent variables in model C2 for psychological contract breach as the dependent variable, and also model D2 with turnover intentions as the dependent variable. So as we can see here, they're positive correlations, so results suggest, or positive betas. So results suggest that more individual level budget cuts, so more personal impacted budget cuts, were a predictor of more psychological contract breach and more turnover intentions after controlling for departmental budget cuts or departmental impact, because those are all entered in the model. However, after controlling for individual level budget cuts, departmental budget cuts are only a predictor of more psychological contract breach, not turnover intentions. Here you can see the explained variance at the bottom, or the effect size. So from the model in D2, we see that individual and departmental level budget cuts combined predicted 15% of the variability in turnover intentions, or in the differences in wanting to quit. Now, if these tables made you panic, don't. Journal articles often include a full written summary of results in the results and a summary of key results in the abstract and discussion. So even if after all this stats review, the tables don't make sense and they just give you a sense of dread, you can just read the article and figure out the results. But I like to go straight to the tables. It just saves me time. So now you can go ahead and take a moment and look at the excerpt from the journal article that talks about those main effects. Again, just looking at, the independent variables predicting the dependent variables. So you can see that usually in the results we talk about which hypotheses were supported or not supported, and you can see that it spells out that individual perceived personal impact was negatively related to job satisfaction, affective commitment, positively related to psychological contract breach. And then you see down here the main effects for departmental impact summarizes the regression model really nicely. Departmental impact was negatively related to affective commitment and positively related to psychological contract breach. And so to figure this out, it helps to know what a positive and negative relationship is, but overall you see that it's explained right there for you. If you're being tasked with summarizing research on your own, it's really important that you don't rely on copying and pasting the summary of results from the journal article, because that is plagiarism, and that also doesn't show anyone that you know what you're talking about. So the best way to do this is to make sense of it on your own. I like to draw flowcharts and pictures and see how things are related. That's just how my mind works. And that helps me then write a more simple explanation in your own words. So you can see I kind of visualize that here, where you know from the regression analysis that individual budget cuts are a predictor of less job satisfaction, less affective commitment, more psychological contract breach, and more turnover intentions, even after controlling for departmental impact. But departmental impact was only related to affective commitment and psychological contract breach after controlling for the individual impact. And you can see there, I wrote a more simple explanation of the results. And instead of talking about affective commitment, I said, they're less emotionally attached. Instead of saying turnover intentions, more interested in leaving the organization. Instead of saying psychological contract breach, I said they felt that promises and expectations were not met. And then I cited it because you always want to cite when you're talking about somebody else's work. And if you weren't sure how to simplify the name or the descriptions of these kind of complex constructs, you can look in the methods section of the journal article, and it will give you a sample item of how this was measured, and it'll give you a simple explanation of what the construct is. So just kind of notice that this isn't what's in the article, but it is a simple way to think about the results. And at the end of the day, that's the goal you should have for yourself, is being able to look at results and then make sense of it and put it into your own words in simple language. Now let's take a look quickly at two really sophisticated types of regression analyses. And with moderation, we'll spend a little bit of time on that because that was actually in the journal article that we're focusing on. Moderation and mediation are both something that you will likely find in journal articles when you're reading them. So I hope that this makes sense and you see the possibilities of these types of analyses. So let's start with moderation. These are called interaction effects. And moderation allows you to look to see if the relationship between two variables differs based on another z variable. So in this example, we can maybe say, does the relationship between workgroup diversity, our x variable, our predictor, and creativity, our y variable, or our criterion, our outcome, so does the relationship between workgroup diversity and creativity depend on the openness of group members? So that would be our z, or our control variable. Another example could be, does the relationship between budget cuts, x, and job insecurity, y, among professors depend on tenure status, whether or not you have tenure, right? Because once you have tenure, you shouldn't have job insecurity because you have pretty much guaranteed job unless you do something awful. Another example that we could use moderation for, does the relationship between individual impacts of budget cuts and affective commitment depend on departmental level impact of budget cuts, which is what you'll see here in a little bit. So again, looking to see if the relationship between two variables differs for different groups or kind of depends on a third variable, z. Now we're going to focus on the final model, A3 and B3, because this includes the interaction term. And you can see that, let me highlight that for you. Usually that's denoted with something times something, right? So this is personal impact by departmental impact. And when you create that in the analysis, you actually do multiply the two scores together. So that makes sense. And so as you can see here, there is a significant interaction for personal and departmental impacts of budget cuts working together to predict job satisfaction and affective commitment. Remember, our dependent variables are up here. So the relationship between personal impact of budget cuts and these outcomes depends on the departmental level of budget cuts. right? It depends on what kind of pond you're in, if you're thinking about the frog pond analogy. It depends on relative deprivation, right? How much budget cuts are the people around you experiencing, and that's going to influence how your own budget cuts impact your outcomes. And that's what those little stars tell us, because that means it's a significant moderation effect or interaction. And now, as you can see here, there's a significant interaction for personal and departmental impact of budget cuts working together to also predict psychological contract breach and turnover intentions. So the relationship between the personal impact of budget cuts and these outcomes depends on departmental budget cuts. And if you look at our squared or our explained variance, now this tells me that 28% of all the differences in psychological contract breach are like perceived, how well people perceive that the promises that were made to them have been met. 28% of all the differences in that psychological contract breach can be predicted by personal impact, departmental impact, and the two put together. So just to give you some more tips on how to make sense of this on your own, I made you a visual of all the significant results. So I only include lines and values for those that were statistically significant, less than a p-value of 0.05. At this point, we know a significant interaction or moderation effect exists, but we need to plot the regressions for the standard range if x was plus or minus 1 standard deviation from the mean, to visualize the direction of the results, to see how the results actually look and how they played out. So again, we know that individual and departmental budget cuts interact to predict these outcomes, but we don't necessarily know the nature of what that looks like. So now let's take a look at the interaction plots for affective commitment and for psychological contract breach. So you'll notice that the x-axis, the vertical axis, represents your dependent variable or your outcome, and the x, or the horizontal axis, represents the independent variable, which is your predictor. So we look here and we see that along the x-axis, that represents values that have a low or a high value for the independent variable. And so those are dictated by 1 standard deviation above and 1 standard deviation below. All right, the appearance of the lines represents the moderator variable. So again, low and high is plus or minus 1 standard deviation. And because our moderator variable in this case is departmental impact, the dotted line represents a low departmental impact, and the solid line with squares represents the high departmental impact. So here we can see that the influence of personal impacts of budget cuts is stronger when the employees are in departments less impacted by budget cuts overall. So the dotted lines have a greater slope, you'll notice. So it looks like employees who experience a greater personal impact of budget cuts, but are in a department that is less impacted by budget cuts overall, tend to have worse outcomes, or in this case, lower affective commitment and more psychological contract breach, than employees who experienced a high personal impact of budget cuts, but also worked in a department that was experiencing a high degree of budget cuts as well. They're kind of in it together. You know, they don't feel like they're experiencing something uniquely crappy for themselves. Everybody else is kind of in it too and experiencing budget cuts. Now, if you find it difficult to make sense of these figures, don't panic. You will get a summary of results in the results section and often in the abstract and discussion of a journal article. So here you can see the summary of key findings. So individuals who perceived greater personal impact of budget cuts, but were in departments where the department head had reported fewer budget cuts, had the worst outcomes, right? And we just kind of saw that in the figures. It's also important to learn how to write this stuff in your own words with citations. So you'll notice I cited Zhang et al. 2014. And you can see that I tried to simplify it here. So you can just take a moment to maybe go back, look at that table again, look at the findings from the article, and then look at my explanation that's a little more simple and taking some of those complex constructs and putting them in simple terms. Now, although we didn't do it in our research, mediation effects or indirect effects are something that you're probably going to see in research. So I want to cover them here and show you an example. So mediation can also be tested with regression analyses, but instead of seeing if a z variable or other independent variables or control influence the relationship between x, your quasi-independent variable or your criterion, and y, your dependent variable or outcome, like moderation, Mediation analyses allow you to see if the relationship between X and Y is direct, so X directly predicts Y, or if it's indirect, where X predicts Z, Z predicts Y, but X does not directly predict Y. So for example, you could ask, is there a direct relationship between work group diversity, X, and creativity, Y? Or does work group diversity influence openness of group members, which would be Z, which then influences creativity? So that would be an indirect relationship. If that green arrow wasn't significant and only the black arrows were, that means that diversity leads to openness, which then leads to creativity, but there's not a direct relationship between diversity and creativity, is what that would suggest. So here's another example of what mediation could look like. And this was not in the study, but we could have tested this with our data. So we could have seen if there is a direct relationship between departmental impact of budget cuts and job-related outcomes, or do departmental budget cuts influence individual level impacts of budget cuts, which would be our Z variable, which then influences job-related outcomes. So it would be a different type of model we could have looked at, and that would have been a mediation model instead of a moderation model. Now, I know this chapter is hitting you hard with statistics, and I know that statistics can be kind of anxiety provoking for people, but please know that knowledge is power, and being able to make sense of this stuff is going to really help you, not just in this class, but beyond this class and beyond school, frankly, because we are presented with numbers and results and research all the time, and it really helps us make better decisions and maybe not click share on something if it's correlational and the title makes it seem causal, and just be a more responsible steward of knowledge and just be better prepared to handle the world and all the information that's thrown at us. So I hope this was useful for you beyond reading the textbook, and you feel more equipped to look at complex tables of statistical analyses and make sense of them. And just remember, regression is leveling up correlation and using it to make predictions about dependent variables in the population. And if you would like to check out the full version of this journal article that we looked at today, go ahead and use the reference and look it up and find it.